Hello everyone, my name is Xinbo Ban. I'm going to talk about the paper TAESim, a testbed for IoT security analysis of trigger action environment. Firstly, I'm going to introduce some background and motivation of the research, and then I will present the simulation testbed, the challenges and the overview. Next, I will present the evaluation and the case study. And lastly, I will play a video, a 1-minute demo. Internet of Things is an emerging communication paradigm that aims at intensively connecting different kinds of objects to the internet. It provides increasingly complicated functionalities and significantly enhances the autonomy of the smart home, smart industry, and smart city. As shown in the figure, the number of IoT devices worldwide is forecast to almost triple from 8.74 billion in 2020 to more than 25.4 billion IoT devices in 2030. Trigger action programming is the most popular framework for IoT programming, which enables non-technical users to express their intent in automating IoT devices. A trigger action program specifies that when a certain triggers event occurs, like motion is detected, one or more actions, like turn on the light, should be subsequently executed. There could be a condition in the TAP rules. TAP has been widely supported by many commercial IoT platforms, like FTTT, SmartThings, and Zapier. With TAP, IoT systems are controlled by event-driven apps. TAP is in the form of if that triggers occurs, then perform the action. Given a TAP rule, IoT system will automatically react following it without user involvement. Multiple rules can be trained as the execution sequence. Here is a typical smart home environment. As you can see, there are many smart devices like connected bulb, smart thermostat, connected window. All devices connect to a centralized hub. Your smart devices can communicate through the hub using a traditional wireless network, such as Wi-Fi or Bluetooth. We call this interaction cyber interactions. However, they can also interact with each other through physical environment. For example, an opening window can change the illumination in the room and affect the smart bulb. If the window is opened, the temperature may also be affected and then trigger the smart thermostat. This kind of interactions is called as physical interaction. The physical interactions of the smart home devices are necessary and they could bring significant convenience to users. Why TAP introduces new security and safety issues? The complex rules introduce a large understanding space to users and express their intent in the cyber world and result in security and safety risks due to rule chains. For example, a room has two states, arm state and home state, and we have three rules. If the motion is detected, then turn on the light. If the motion is detected when the house is in arm state, then send a notification. And if the light is turned on, then set the house to home state. And we can say there would be two rule chains, and the rule 2 will cause action, send a notification, which is unexpected. So the unexpected interactions and the interferences of tier rules may give rise to severe vulnerabilities in an IoT deployment. For physical interaction, if, for example, we have two devices, the smart window and the heater, and the first rule is the if time is after 18 o'clock and then turn on the heater. The rule 2, if the temperature is higher than the 35 degrees, then open window. And these two rules would interact with each other and result in an unexpected consequence, which is window is opened when user is not at home. So there are two attributes in these two rules. So it is an unexpected consequence and it is risky. The recent research has improved the IoT safety and security. One option is to manually inspect deployed DAP system. It requires the domain knowledge and lots of time for the researcher. And many works utilize model checking to verify whether the rule chains violate the specified property, but the process of checking has no runtime and physical environment information. Thirdly, the dynamic testing could obtain the physical environment information, but it has to purchase the devices. So we are motivated to produce a simulator of a real TAP environment to capture the runtime information and all interactions for large-scale analysis. Based on this insight, I propose and implement a simulation testbed to support TAP environment modeling in the research of IoT safety and security. In order to properly model the IoT environment, we discuss the challenges that a simulation testbed faces. First, it is a challenge to simulate the real physical environment. For example, how to model the temperature and the illuminance in different weather. Second, IoT rules usually enable device to act based on the trigger and the condition, how to model the behavior of the device. Third, we need to set the initial value for the environment. Furthermore, the many IoT rules co-work together and interact with each other. So how to model the behavior of these rules. And lastly, the IoT rules have to connect to the devices. To model the trigger action environment and address the challenges, we use MATLAB Simulink as the simulation engine because it fits the requirements of the proper discrete event simulation. MATLAB is a programming and a numeric computing platform for model creation. It integrates Simulink, that is a block diagram environment for multi-domain simulation and model-based design. In the testbed, I need to consider this component. The device state is modeled as a public variable using a data store memory block to store the numerical value 0 and 1 to represent the state of the device off and on. The rule is modeled as a switch. For example, if the motion sensor is detected, it triggers the lights to turn off. A rule could change device states and environment variables. About the channel, for example, cyberspace channel time, physical channel temperature, the values are stored in the data store memory block as well. And importantly, the channel modeling is based on the real environment. For example, the testbed must consider the heat loss, outdoor temperature change, thermal resistance of house, and so on. About the device, most devices have two states, on and off, and we use the data store memory block for saving the state. And the device impacts cyber channel and the physical channel. We adopt the heater simulation from official Simulink website, and the model of the heating influence can be described as follows, where dq divided by dt represents heat flow from the heater into the room. C is the heat capacity of the air at consistent pressure. M dot is the air mass flow rate through the heater. And T heater is the temperature of the hot air from the heater, and T room is the indoor temperature at the same time. The rules need a switch and a terminator. For example, this rule. It means if the motion sensor detects movement instead of light. This block is the state of motion sensor. If it is 1, it means motion sensor is triggered and it triggers action. If else, do nothing. Then it changes the light through the cyberspace channel. About the channel modeling, firstly, cyberspace channel. I designed 2 cyberspace channels, time and hold mode. For example, Simulink provides a time function block to represent time. And about the physical channel modeling, it is similar to the cyberspace channel modeling, but it needs more environment information. For example, I use a hot heat system model to explain. This is the equation of the heat loss. At the left of the equation is the heat loss from indoor to outdoor. T in is the indoor temperature, T out is the outdoor temperature. Req is the equivalent thermal resistance of house. And this is a subsystem of the heat loss. For evaluating the efficiency of the testbed simulation, we tested the average simulation time of the different stop time setting in groups of devices. I created 6 groups with different numbers of devices. The first simulation has 10 devices, and accordingly duplicate them to create the simulation with 100, 1000, 50, 500, and 5000 devices respectively. Different stop time are specified, including 60 and 360, 720, 1440, 180. The stop time is viewed as the minutes in the simulation. We ran each test 10 times in each group and reported the average result. As shown in figure, the time consumption of the stop time 60, 360, and 720 for the 4 groups. Device 10, device 100, device 50, device 500 is 1 second in real world. And the time consumption of stop time 1440 for them is 2 seconds. In summary, this testbed could deal with the large-scale simulation within a few seconds. A case study for evaluating the effectiveness for testbed, given 2 rules, 1440 start time and random initial temperature from start time 0. The x-axis for this figure is time and the y-axis is temperature. It shows the heater is turned on from the beginning and the air conditioner is turned on at about time 180. It violates the property heater and the air conditioner must not be switched on at the same time. It successfully detects the security violation in the simulation. We also create a demo for this case study. Please see this 1-minute demo. This is a short demo to show the TAESim, a testbed for IoT security analysis, and the case study can be found in the paper and the presentation. Up in the left-hand corner, there are the data store memory blocks for sharing public variables. On the upper left-hand corner, there are the subsystem for the several channels. And we have 2 apps. If the room temperature is higher than user's input, then turn on the heater. Another one, if the temperature is greater than a threshold, then turn on the air conditioner. There is a dashboard for the demo. We could set a threshold for heater and air conditioner, and we could see the TAE environment, trigger action, and we could see the trigger action environment. White for the device state, white represents the off state, and the green represents on state. Now we run this. The start time is 1440, and we can see the temperature change. We can see the temperature changes because of the temperature daily change and the devices. A violation occurs because the heater and the air conditioner are turned on at the same time. Thank you for listening. I'm happy to answer any question.